Welcome everyone to the first seminar of the fall semester. And today it is my greatest pleasure to introduce the topic on soil, which is a research topic for myself. And Dr. Mielke here is opening the season on soil and bloodlet data that's related to health and environment. And we met with him the first time about 3 years ago in New York in person. Before that, I have been his fan for many, many years because he is one of the fathers of establishing knowledge, like really research on environmental signaling, and established for the first time association between bloodlet levels in children and soil health. So today he will share his insights on his life journey, but most importantly on his research. And he dedicated his life to study this super important topic. He came to us from Tulane, from New Orleans, very close. So I think you will take it really close to your heart that to know more about the area we all live in. So welcome to Dr. Howard Mielke, who will speak for another hour or so, and you're welcome to ask him any questions at the end.
Thank you very much, Dr. Balti. Maybe I can hear myself better this way too. So I want to start by just introducing my little journey that I've taken over the years. It's been a peripatetic type of journey, meaning that I walked or really traveled around a lot as part of my research. And so I've been to many different places, and we'll start with Peru. Peru is there's a major mining site in Peru, and the place is called La Arroyo. It's located in the mountains, and it's one of the largest smelters certainly in North America and South America. And it has a lot of planetary implications, as you will see. I will then switch to urban scale environmental signaling. Environmental signaling is what I'm doing in the School of Medicine at Tulane University. And it refers to the kind of signals that human beings pick up from the environment and its influence on health. And I will demonstrate that as we go. So we'll start with world scale, just to give you a sense of the Earth scale of the movement of materials and the geochemistry that has been taking place and developing as a result of human industry and mining industry and smelting industry. Now, this particular site is, as I said, a very large smelter, and it's being smelted for a number of different metals. So the geochemistry is related to, of course, what is being mined out of the earth. And these are some of the metals that are important. The ones that are especially toxic include arsenic, lead, antimony. There is some bismuth. It's not very toxic. And the ones that are important in the mining industry, of course, silver and gold. And these are coming out of the smokestack. They're not controlling it very well. And part of the problem that we have, and this is going to be a constant issue when we start looking at lead in the urban environment, especially, it's particle sizes that are invisible. So here we are going to be talking about something that we can't see, and for a long time we weren't really able to measure it, and I'll describe that. And the particles, compared to the human hair, the particles that are particularly toxic are the ones that are less than 2.5 5 microns in size, in micrometers. So those are part of combustion products that are associated with smelting and associated with such operations as automobile exhaust, and we'll talk about that. So inhalable, absorbed directly into the bloodstream, very fine particles, and we have good evidence for that. Now, this particular smelter is easily seen from space. It's located right here, run by Doe Run. And you can see, because the sulfur dioxide is one of the substances in the atmosphere, you can see that. But then you start looking at the Northern Hemisphere, we have China and India, and certainly places in the Middle East, in North Africa, an enormous amount of material going into the air. And this is a worldwide distribution of substances. And what we're looking at mainly is sulfur dioxide. But along with that, of course, is carbon dioxide and a lot of very fine particles of that. Okay, so on the urban scale, the global scale, and I worked with NASA for a while, so I have good imagery showing the global scale of various substances in the environment that have been released into the air and are showing up through the global environment. On the urban scale, the issue became, I'm working with an invisible substance. How on earth can I possibly say anything about something that's invisible? And it was invisible because we didn't have the equipment at first. My research odyssey then, I love this statement by George Wald. The rationale of experimentation is like a quiet conversation with nature. One asks a question, gets an answer, then one asks the next question, gets an answer. An experiment is a device to make nature speak intelligibly. After that, one only has to listen. And so I will talk about a series of experiments that I was involved with in many different places that helped put together a picture of an invisible substance. So the first part of my just understanding that there might be a problem came about as a result. I taught at UCLA, and I had large classes, 300 students. And so these students, it was a commuter campus, and I was interested in how much mileage they put on their cars. So in the first day of the semester, there's a quarter system there. The first day of the quarter, I asked everybody how many miles they drove to school and how many times a week did they do this. And what I started realizing is that if you think in terms of the miles that were driven, I could calculate essentially calculate the amount of automobile of the fuel. It was leaded fuel at the time, and the leaded fuel could work out the grams. The grams, I have it here as millions of micrograms. Gram is a billion micrograms, and it's 61,200 grams, or 61,200 million micrograms of lead. Now, what does that mean? Well, we're worried about the exposures that for a human being, for example, much less than 5 micrograms per day from all sources. So this is an enormous insult on people who are breathing in the city of Los Angeles. And that was my first indication that maybe there was something really wrong here. So you don't have to go too far, although it's hard to get the literature, which is kind of a tragedy. I didn't find this literature until rather recently, it happened to be in the Tulane library, the medical school library, and it was hidden by changing the name of the journal and just got put into shelves in a strange way. The literature was from the proceedings of the conference to determine whether or not there is a public health question in the manufacture, distribution, or use of tetracthyl lead in gasoline, leaded gasoline. And this was both public health bulletin and a Treasury Department bulletin. So Treasury Department, what's the Treasury Department doing with health issues? The US public health wasn't the only one involved. And it turns out it's because of the enormous income, the economics behind putting lead into gasoline. So here's a good quote from somebody who was at the hearing. That some conditions will grow worse so gradually, and the development of lead poisoning will come on so insidiously that leaded petrol will be in nearly universal use before the public and the government awaken to the situation. And at the time I was working on this, it was not public information. We really had little idea what was taking place. And Yale Henderson went on to say, a Yale professor, Yandel Henderson, this is probably the greatest single question in public health that has ever faced the American public. The question whether the action of government is guided by scientific advice or whether commercial interests are allowed to subordinate every other consideration to that of profit. And it's a profound statement. We're still struggling trying to work on arranging or understanding, first of all, and then dealing with the substances that are being released into the environment. So fundamentally, we were really not able to measure lead in the environment until a geochemist introduced us to mass spectrometry that he had learned to use as when he was working on the atomic bomb project back in the 1940s. And basically what he, after that project, Manhattan Project, he turned his attention and his scientific work into looking at the amount of lead in the environment. And he did this by looking at the amount of lead showing up in various layers of ice within the Arctic, Greenland, and also he went to Antarctica to do the same thing. And he started realizing that old ice had very little lead in it, but the newer ice had a large amount of lead. And he said, there's a problem here. We're getting an aerosol that is being distributed across the planet and at an alarming rate. The other industry, or the industry that was involved, of course, was the Ethel Corporation. It's in Louisiana, or it was in Louisiana, in Baton Rouge. And they wrote a paper that was published in a very important journal. It's called PHP, Environmental Health Perspectives. And in that article, they claimed that the lead that was being found in soil was only related to the lead paint on the buildings, and that the automobile, the distribution of lead into the environment, did not play a role in the contamination of the soil. So this was 1975 or 74 that article was published. And to begin with, that was an article that I became very concerned about it, because my understanding was that there was a lot of lead being introduced into the environment as a result of travel. And I learned this from my students at UCLA in Los Angeles. So with that kind of background, we then had to figure out what to do. And meanwhile, Clair Patterson had some very important information. And he basically realized from his studies on ice cores that there was a lot of lead in the atmosphere, but it was accumulating mainly in cities. And his statement is sometime in the near future, it probably will be shown that older urban areas of the United States have been rendered more or less uninhabitable by millions of tons of poisonous industrial residues. My question is, are his concerns really warranted? Is there evidence for this? He didn't have any evidence. He didn't really go out and measure the amount of lead in the urban environment. What does he mean by uninhabitable? We're living in cities. How are these uninhabitable? So we have to go one step further and realize that meanwhile, there were people in health, the health community, environmental health community, that were looking at things, that issues like learning and violence of people who were exposed to lead. And we started realizing that there was, in fact, a human relevance behind having exposures to lead, an invisible substance. So in the mid-1970s, what I started realizing is that we needed to put we had to have skills to be able to measure the amount of lead in the environment. And this involved analytical tools, statistics, and computers. In the mid-1970s, all of this was still being developed. So let's start with the analytical tools. In the medical community, the analytical tools that were developed were applied to measuring the amount of lead in the blood. And we still have that bias of measuring lead in the blood. And when I first started my work, it was colorimetric methods. And the best we could do is 60 micrograms per deciliter. Now that won't ring any particular bells to you if you're not familiar with the health issues regarding lead. But 60 was the standard, and the government developed then a standard based on that ability to measure at 60. Then some new equipment became available, new instruments, and these were based on the atomic absorption spectrometry. And atomic absorption spectrometry, we could measure 40 micrograms per deciliter. And then they became, some work was done by a colleague of mine on the electrochemical methods. And he found that he could measure 30 micrograms. And as you look over the years, that's when we changed the standard of what we thought, the guideline of what we thought was safe, to 30. Then came the graphite furnace, and that was much better. And then the standard went to 25. Then we had the inductively coupled plasma mass spectrometer, and this is atomic emission rather than atomic absorption. And this allowed us to measure at 10 micrograms per deciliter. So for many years, the standard was from 1990 to, I think this is around 2015 or so, 2012, that we realized that lead in the exposures at that level were terribly important. Now we have point of potential exposure with the XRF, the portable XRF. And I use the portable XRF. I've been working very hard at trying to understand how the XRF matches with other techniques that have been used. And we discovered, in fact, that there's amazing similarities in the the results that you get from different kinds of methods. So we had the reference value, which is now 5 micrograms per deciliter. But I expect that in the future, the exposure levels will be dropped to 3.5 micrograms per deciliter. And so that's under discussion right now in Centers for Disease Control. So the instrumentation was extraordinarily important. We couldn't even measure these fine, the levels that were important in health. And I'll show you some other materials about kinds of issues that you have. Statistical tools. Of all, serendipity played a major role, and synchronicity was a major role. And I couldn't do my work until instruments were developed. I couldn't do my work until better statistical techniques were developed. And of all things, I have a brother, or had a brother, he died recently, who was a statistician, and he was working with a form of statistics where all of the data that is being collected is being used in evaluating the statistical significance. And so he was a very strong critic about the ordinary statistics that are often used, the ANOVA. And he said, the problem is that there are false assumptions. And when you have a false assumption, we're depending on that there's going to be a normal curve. And what we try to do is change our data so it fits a normal curve. And when you do that, you've changed the data. And he was very critical about that. And you're not working with data that you have. And he developed a form of statistics called multi-response permutation procedure, which resolves all of the issues that we normally have with statistics. And so Paul, my brother, Ken Berry, his colleague, and myself worked together audaciously to challenge statistical practices. And of course, I'm still involved in that program, in that project. And then we come to computers. Back in the 1970s, we were stuck with horrible ability to measure anything or to store data and to use the data. The best we had actually was computers that we were using were Cray computers in the 1970s, and these were very high-powered computers. I think they're used for benches right now, but in the past, they were the best computers we had. And GPS was not available. We couldn't go out and get XY coordinates. I mean, today, walk around with a phone, you can get an XY coordinate. You have Siri telling you where to turn, which corner, those are all based on GPS. So the analytical instruments, the data sets that we were putting together, statistics and GIS software, and the computers were all important in the development of the work that I've been doing. So let's take a look at how we use this. The first major project that I did was in Baltimore, Maryland. And we were trying to understand the extent of lead accumulation in cities. And I worked with the US Department of Agriculture. My colleague was Rufus Cheney. He's a brilliant chemist, and we worked together to develop a method of measuring the amount of lead in soil. And Baltimore was a perfect place to work because we had the inner city, which because of a fire that took place in 1904, was rebuilt with brick city. It was brick and stones in the inner city. The outside of the buildings are brick and stone. And the outer city is lead painted wood. And so what we expected to see, according to the literature from the AHP article by the Alpha Corporation, was that we would find high lead levels in the areas of the city which had painted buildings and low lead in the areas of the city that were stone buildings. And so that was a contrast. And here's what we found. The map, we were mapping 1983, mapping the city. This is actually from an article that finally got published in 1983. We had data together in 1979. We couldn't publish our work for anything. But in 1983, the Journal of Public Health finally published it. And what we found was that if you work with the medians of the amount of lead and then just look at the city in terms of what's above the median and below the median in the locations, what we discovered was that there was a remarkable difference between the amount of lead in soil in the outlying areas of the city and the interior of the city with the brick and stone buildings. And it turns out that the p-value, which I hope will make sense to some people, it was 10 to the minus 23. My brother was always trying to help me understand how to explain this to an audience. You would have a better chance of throwing a ball to the moon than is observed in these data. So it's a phenomenally small chance that, or small odds that chance alone explains these data. So as a result of this, I looked at it and said, well, gee, if you're seeing this kind of difference in a city like Baltimore, it must be something that is similar in other cities in the country. And I was given the opportunity by my institution to change jobs. And I went to the Midwest, which is where I'm from. I was then involved in looking at large cities in Minneapolis and St. Paul. And it turns out that while I was doing the work, a physician approached me and said, we're having a problem with the new immigrants that were coming into the Twin Cities. They measured the blood lead levels of the Hmong people as they came to the airport. And I don't know why they decided to do this, but they did. And then about a year later, they measured the blood lead again, and they found a very steep rise in the amount of blood lead. And he said, well, why is this steep rise taking place? These were buildings that they'd been cleaned out, they'd been repainted. There shouldn't be any lead-based paint showing up as a problem in these houses. But it turns out, as I spent time with Hmong families, they would, during the day, in the summer day, the family would sit on the front steps and the children would play in the soil right next to the steps. And I started thinking, uh-oh, they're getting exposed to lead as a result of the soil. And it's not just a paint problem, it's more than that. And so we started mapping the city, and then the legislature also contributed to this. And they had a wonderful project looking at soil and children's exposure using blood lead. And what we found is that the amount of lead being found in different cities across Minnesota, the largest cities had the largest amounts of lead, and the smaller cities, such as St. Cloud and Rochester, had very small amounts of lead. Well, the interesting thing about Rochester is that that is a very old city, Rochester, Minnesota. It's where the Mayo Clinic is, and it was settled early, and it has a lot of painted buildings with very little children, or the soil wasn't coming up with a lot of lead. And it turns out that when we started looking at the exposure in these different cities, it followed the same pattern that we were seeing in the soils. So the influence, what we were interested in, is several different characteristics. What were the processes that caused lead to accumulate along the sides of buildings? And what we started to realize is that atmospheric lead that was exhausted and into the atmosphere, would then float, hit the sides of buildings, and then it would wash down the sides of buildings. So this represents automobile traffic, and the buildings that are very near the highway would have very large amounts of lead on them, even if they were brick buildings. And as you went further away from the traffic, then there was less lead. And in between, there was a constant reduction taking place in the amount of lead in the soil. So the accumulation around buildings, which was pointed out by the Alpha Corporation, is partly related to the product that was being used, the leaded gasoline that was being used in automobiles. And so next to buildings, even if they weren't painted, you could find a lot of lead. And this is the kind of situation that I kept finding in the Twin Cities in Minneapolis and St. Paul. Sandboxes near the buildings, very high lead. And it was clear that children had been playing in this sandbox. And I measured the amount of lead, and I discovered very high lead levels. So blood lead in Minnesota cities, by size of the city, Minneapolis had most children with the highest blood lead, and the least children with the lowest blood leads were being found in Rochester, Minnesota. And it followed the same pattern that we're seeing in the amount of lead in soil. So we started realizing that that was a terribly important part of the problem that we were having nationally in terms of exposure to lead. Now, we know a great deal about the trends in lead in gasoline. Lead was being taken out of gasoline starting in 1975 because of the catalytic converter. Basically, the concern was that the health of the catalytic converter was being damaged by lead in the fuel. So we had to make a healthy environment for the catalytic converter. They weren't thinking about children's health. They were thinking about the technology, the catalytic converter. But we ended up, of course, realizing that when we took lead out of gasoline, we started seeing these remarkable reductions in the amount of blood lead with the reduction of lead in gasoline. And during the period from 1975 to 1980, there was a remarkable reduction in blood lead in the United States, but it still was pretty high. And there was some deregulation taking place in the early 1980s, and blood lead levels started going back up again. Cars that were designed because they had catalytic converters, they were designed for unleaded fuels, but people started taking out the little restrictor in the nozzle and putting leaded gasoline in cars that were designed for unleaded. And that had a very large effect because it increased the amount of lead in the air and children's exposure. And at this point, we start realizing inhalation is going to be very important. And that's back to the particle size that I talked about earlier. So Minnesota the health department did see this increase, and they started realizing that more leaded fuel was being produced and consumed. So they started looking at the issues. In the meantime, my daughter became lead poisoned. And that triggered just a good parental response on my part. What can we do if children across the entire metropolitan area are being exposed to an invisible substance which was accumulating in the environment where children were playing? And we developed a citizen science, and we called ourselves the Minnesota Lead Coalition. And as a parent, and as someone who knew a lot about lead by that point, that we had to understand how, what, where, when, and why lead exposure was taking place. And we focused in on the use of lead and gasoline. We thought that was obviously something that had to be curtailed. So the Lead Coalition, Minnesota Lead Coalition, was a small, thoughtful, but committed group who studied to understand and act to ban lead and gasoline. Now, our first effort in banning lead and gasoline hit a wall right away. It was illegal for the state of Minnesota to protect its own citizens from lead and gasoline. It was a national issue. And so what we ended up doing was going back to the legislature. We spoke with them, and some really bright people said, well, we'll just petition Congress and the EPA to get lead out of gasoline. So the Minnesota Legislature, because of their studies, they were very aware that Minneapolis and St. Paul, inner cities and outer city soils, the lead results in the environment were similar to what we had already described in Baltimore, that the quantities of soil lead were associated with city size, and that matched the lead and gasoline issue. That Minnesota Department of Health found that children's blood lead was associated with city size, and of course, the amount of lead in the soil, the accumulation, and high school dropouts. They went further. They looked at high school dropout rates where there was very small amounts of lead compared to places where there was a large amount of lead. And they discovered that it was associated with city size. And that became very concerning to the citizens of Minnesota. And so the Minnesota Legislature tried to ban lead and gasoline in Minnesota, couldn't do it, it's illegal. So they petitioned Congress to ban lead and gasoline. And the hearing took place on June 22nd, 1984. This was an abstract of I was invited by the state of Minnesota to represent the citizens, the legislature, and the children of Minnesota. And basically, my testimony came down to the tetracthyl additives were a major source of lead dust in the cities, and that federal law prevented our state from doing anything about it. So that's why we went to Congress. The children were at highest risk. We understood that. They were suffering from diminished health, and there was already some indication of that, especially in education and violence. And for a society to flourish, adults must address the needs of the children. And so the Lead Coalition supported a bill at the House that we basically have a rapid phase down January 1st, 1986. Well, there was an enormous amount of pushback on that whole issue. Tetracthyl lead was a legal product. Government can't willy-nilly eliminate a legal product because of some crazy guy in Minnesota at McAllister College saying it was a problem. But ultimately, we won the case, and rapid phase down took place January 1st, 1986. And so with that, I was invited to leave Minnesota and to go to New Orleans. You don't always win friends when you do something a little radical, but it's it ended up being part of my journey. And so I started the same research in New Orleans. I was at Xavier University. I was invited to be in the College of Pharmacy, working on environmental health issues. And so we started paying attention to this whole idea that the city of New Orleans has such extraordinary traffic flow into the center of the city. So I started mapping the city And we knew something by then because of the hearing about how much lead was actually put into gasoline. We started, comparing with lead in paint, and most paint is still intact on buildings. Don't sand it off, for heaven's sakes. That makes small particles. It just creates problems. Instead, you have to wash the building and then paint with some of the new, very good paints that were developed actually in Europe. And when we look at the amount of lead, we started realizing that lead in gasoline was an amazing peak that took place in 1975. It started coming down, and then the rapid phase down in 1986. A very rapid reduction took place. And paint is still on the buildings. But it's easy to work with compared to the fine dust particles. So the rise and fall of lead dust has become an issue. And a lot of the rise and fall took place in 1950 when, for some reason or another, people got, the industry got together and said, well, benzene was in gasoline, that was causing cancer problems, so let's move to lead in gasoline. So we moved to lead in gasoline in 1950. And that's when the very rapid increase took place as a result of increasing. It was at the same time that highways were being built and automobile economy became very important. So my team and we've been together since Xavier days. Chris and Eric still work with me. Eric did all of the collection of samples. He was really good in the field. He had a lot of experience working with different people throughout the city of New Orleans. He knew New Orleans very well. And then other students were involved in these projects. And we were collecting samples across the entire metropolitan area. And we also knew that Louisiana's results were very similar to what we were seeing in Minnesota. The largest city, New Orleans, had the highest amounts of lead in it, and the smallest city, Natchitoches, turns out to have a very small amount of lead in the environment. Makes sense. It doesn't have a lot of traffic flow, has a lot of buildings, a lot of lead-based paint, but very small amounts of lead in the soil. Okay, so the result of the New Orleans soil lead, these are the results by distance, basically, from the center of the city. And in the highest lead areas of the city, we were finding 400 to 17, over almost 1,800 parts per million as a median. So there were a lot of samples that were higher than that. And it's a very contaminated area of the city. It's a lot of the city, interior of the city. Then the lowest amount of lead was being found in the outlying areas. So how does this square with the blood lead? I worked with the health department, and they provided the blood lead samples from thousands of children. Taking blood regularly from children, supposedly to help them with the health. Unfortunately, taking blood is secondary prevention, not primary prevention, because by the time you measure the amount of lead in blood, it's too late. You've already gone past their exposure. And so we wanted to look at the environment. That's use the same instruments that have been used to measure blood lead to measure the amount of lead in the environment. So here are the results for blood lead. These are the results for soil lead. And you'll notice that there's a very strong association between the amount of lead being found in the soil environment and the amount of lead being found in children's blood across the city of New Orleans. And when you graph this out, a lot of children, their median blood lead was actually, let's see, we don't have a scale on here for, oh yeah, we do. you notice that early on, over half the population had blood lead levels that were above 5, and especially in the higher soil lead areas of the city. There was a very steep rise in blood lead at the lowest levels of lead in the environment. And that was a major concern. If you really want to counteract a steep rise, you have to have a very strong guideline for how much lead, a safe level of lead in the city. And what we started realizing is that a safe level is probably around less than 40 parts per minute. And our current standard in the United States and a lot of the world is 400 parts per minute. Well, you can't possibly have a safe environment with a margin of safety at anything above 100 parts per minute. We think with a margin of safety of about 40 parts per minute. So moving on, the relevance to human health over 10 years, from 1976 to 80, 1988 to 91. These are graphs showing the amount of blood lead being found in children in 1976 to 80 compared to the amount of lead being found in the blood of children 1988 to 91. Notice how different these curves are. And what was considered safe as 10 in 1990 has proven to be unsafe. Now we know that less than 5, probably 3, maybe even 1 micrograms per deciliter. I'll show you some data on that. So age of peak exposure, somewhere around, looking at 18 to 24 months. That's peak exposure. And the children that are living in the high lead environments have highest peaks in the low lead environments. This is from research from Cincinnati. Okay, now comes the juicy part in terms of what we understand about health. I'm going to show you 2 videos. One is by Dr. Kim Cecil, which talks about the irreversible fetal brain damage resulting from lead exposure. And the second video is going to be on coronary heart disease by Dr. Bruce Lanfear. And both of these people are outstanding in the field. So you can see that there are a lot of different characteristics associated, health problems associated with exposure to lead. Let's take a look at what Kim Cecil says. Do we have sound? How do I get sound? Forgot. Oops, that works. Don't have to just go back. All right. Sorry, let me go back to the previous slide. Sorry, I'm still, I'm fumbling a little bit. There we go. Kim Cecil.
Even the ancient Romans who used lead for plumbing knew it was toxic, though they didn't understand why. Today, we do. Cincinnati Children's Hospital and the University of Cincinnati have been following children exposed to lead into adulthood. It's the longest running study of its kind in the world. Dr. Kim Cecil is an investigator for the Cincinnati lead study.
So lead tricks the body into thinking it's calcium. Whenever lead has got into your body, primarily through ingestion, it goes and hides where calcium should be, in the bones and in the cells of the brain. Visualize a neuron. There's the neuron that's sending the signal and another that's receiving the signal. And typically calcium is in that gap.
Calcium is essential for neurons to communicate. But when a child is exposed to lead, lead gets in that gap and blocks the flow of calcium. Without calcium, synapses get weaker and brain function suffers.
The average IQ of the Cincinnati lead study is 86. It should be 100 in a typically developing population.
Lead can disrupt brain growth and even lead to shrinkage or volume loss in brain tissue.
I can give you kind of a hint of volume loss. You can see these ventricles look plump because there's less brain. From this analysis, I can tell you that most of that volume loss is in the frontal lobe. And that region of the brain is responsible for what makes us the most human. It controls our decision-making, our ability to pay attention, our ability to plan, to make judgment, to evaluate rewards, all the things that we need in life to be successful.
Lead can cause harm wherever it ends up in the body. And lead poisoning can even be passed to the next generation.
If you're a pregnant woman exposed to lead when you were a child, that lead is stored in your bones, and when your body needs calcium for the developing fetus, it's pulling lead out of the bone instead of calcium in many cases.
So now what we're starting to realize is that lead exposure in childhood turns into a multi-generational exposure because the storage of lead in the bone, it is stored in the bone and then released during pregnancy, in this case. And for males, there's a little different problem. I think this is males only. Whoops, let me get to it. Oh, yeah.
Lead is a risk factor for coronary heart disease. That's when your heart is slowly or suddenly suffocated by an obstruction of the arteries feeding the heart. In a national study, we found that deaths increased sharply at blood levels below 50 parts per billion, the level considered safe. There was no threshold or safe level. If we let the narrowing of this coronary artery represent the risk of dying from heart disease, you can see that most of the narrowing occurs below 50 parts per billion. We found that lead accounts for about 185,000 deaths every year. That makes lead the leading cause of fatal heart attacks in the United States.
So we're finding, of course, that as there's a reduction in the amount of blood lead, gradually there's also reduction taking place in the death rate in the population for cardiovascular problems. And we've done a lot of work on school performance by the amount of lead in the city. We've also looked at violence in the city, and not just New Orleans, but several cities across the country. And we're seeing that the amount of air lead is about a lag of about 20 some years, 22 years between the exposure from air lead to the curve of violence. And that's been demonstrated by several people now. This is not, I'm not the only one who's seen that. And we know that the amount of lead in the soil represent a huge amount of dust, invisible dust. And we've done this by considering we use what is called a plop sampler. We call a plop sampler. We take an ordinary sample tissue that's normally used inside. We put it on an envelope and turn it over, and then measure the amount of lead that we pick up as if you're putting your hand down. And we find phenomenal amounts of that in the environment. Most recently, we have an article out in PNAS, the Proceedings of the National Academy of Sciences, in which, because we did two different surveys, one in 2000 to 2005, this is blood lead for 2000, 2005, and the second one, 2011 to 2016, and we matched it with soil lead being collected at pretty much the same time. What we have seen is that there's an enormous reduction taking place in both the amount of lead in the soil and the amount of lead in the blood. And that's very encouraging because it says there's something we can do about it. And I'll just skip forward. We wondered if that same decline in soil lead and blood lead was taking place in other cities. And this is when we get to Detroit, because we happen to have a sample set that we collected in 2000. We recollected that in 2019, and indeed, we found the same thing. So I have done some work, a lot of work in Norway, and we found some remarkable differences between the countries. And I won't go into the detail here. I have a Norwegian colleague named Rolf Orderson, who passed away recently. He campaigned for Norway's Clean Soil Act, and they passed it. The Parliament passed the Clean Soil Act. And it was fascinating to me. The only problem is that when they started looking for the amount of lead in the environment, they found very small amounts of lead. We need the Clean Soil Act in the United States. We should be changing our environments, especially within the interior of the city. And we don't have a program of that kind. And so I'm really encouraged to see the development here of a soil lab that is dedicated to the urban environment, urban soils, because measuring the soils and alerting people changes people's behaviors. And Dr. Holtzville has done a remarkable job putting that program together. So we know something about medical relevance, and we have some work to do on the continuing amount of lead being used in small aircraft piston engines, and accounts for, now they're saying 70% of the air lead from the use of leaded fuels in small aircraft. And so we've got a lot of problems and issues that we still need to resolve in terms of just lead. And again, I've suggested that when you do research, you ask a question, you get an answer, then you ask that from that question or that answer, you ask the next question, you get an answer. And an experiment is a device to make nature speak intelligibly. After that, one only has to listen. And that's what we've been doing, is trying to find or see an environment that's invisible to us, and we're trying to understand how that relates to human health. And I hope this gives you some understanding and background as to the kind of work that I've been doing. And